In this PowerPoint, we're going to have a look at modelling with series. So that means that using the knowledge that we have of series, but to real life situations. Here's a quick starter to remind you of some important things about series that we've learned already. So press pause now and have a go, and then on the next slide, I'll show you all of the answers. Here are the answers then. So in question 1, we can see that the first term is 3, the common ratio is 3, and we're finding the sum of the first 20 terms, so we can say n is 20. And then we can use the SN formula, there it is, from the formula booklet, sub in all the things that you know, and we get this enormous answer. Question 2, the third term is 1. So that's AR squared, is 1. The fifth term is a ninth. The fifth term is AR to the 4, which is 9. And we can solve them as simultaneous equations by dividing them. If we divide them, the a's will cancel, and r to the 4 divided by r squared is r squared. So we get r squared equals 1/9 divided by 1, which is a ninth, and then we can square root to get a third. We're given that r is positive, so I've taken the positive square root. Obviously when you square it could have been a negative, but I've taken the positive because it told me in the question that r was positive. If I sub that r back into one of my equations from earlier, then I can work out the value of a. The question was find the sum to infinity. The formula for that is a over 1 minus r. So now that I know a and r, I can sub those in and find my sum to infinity. So here's a fairly basic example of how a sequence could be used in a real life situation. And this is an example of compound interest that I'm sure you remember from GCSE. Imagine you put some money into a savings account which offers 2% per annum, which means per year. So we're starting with £2,000 in the bank. After a year, 2% would have been added in. And the quickest way of working out that total would be 2,000 multiplied by 1.02. And then the year after, we would have 2,000 times 1.02 squared, because the interest will have been added in twice. And then the next one, 2,000 times 1.02 cubed. So you can see that this is a geometric sequence, where the first term is 2,000 and the common ratio is 1.02. So if you wanted to work out how much would be in the bank after a certain number of years, you could use the nth term formula for a geometric series. Notice that after 1 year is the second term in the sequence. If we use 2,000 as the first number in the sequence, the second number in the sequence is how much would be in the bank after 1 year. And then the third term would be how much is in the bank after 2 years. So you need to be careful there that you select the correct term. Here's another really basic example of, this is an arithmetic example. A child receives a Christmas gift of £30. They decide to start saving in a piggy bank. Their granddad gives them £5 each week in pocket money. How much money would they expect to have in their piggy bank after 8 weeks, or 8 weeks after Christmas? So this is a very simple example, but it's an arithmetic sequence, isn't it? They start with £30, they put in the piggy bank, and then if they receive £5 pocket money each week, then their amount is going to go up by £5. So this is an arithmetic sequence. The first term is 30, and the common difference is £5. So if you wanted to know how much they'd have after a certain number of weeks, you could use the nth term formula for an arithmetic. After 8 weeks, it wouldn't take you long to work out how much would be there after 8 weeks. But if that number was much higher, then it would make sense to use the arithmetic formula for the nth term. Getting on to some more interesting examples. Physicists use things like geometric sequences to calculate the amount of radioactive material left after a given number of half-lives of the material. During each half-life, the material decays by half or by 50%. So if we start off with an amount, let's call it 100%. After 1 year, there might only be 50% left. Then after 2 years, we'd have 25% left. After 3 years, it would be 12.5% left. So each year, the amount that's left is half as much. And if we write that out as a number sequence that you can see here, you can see that this one is a geometric sequence. The first term is 100, the common ratio is a half. So it would be very quick if we use the formulas for geometric sequences, we could very quickly work out things like how long would it take for there to just be 2% left, or how much would there be left after 25 years. Those sorts of questions could be answered very quickly using the geometric formulas that we learned when we did that topic. This is a nice example from the booklet. A piece of A4 paper is folded in half repeatedly. The thickness of the A4 paper is 0.5 millimeters. Work out the thickness of the paper after 4 folds. So if you've got a piece of paper handy, you could start with that piece of paper opened up flat. The thickness is 0.5. If you fold it in half, you then have 2 pieces of paper sort of connected together, one on top of the other. It's still one single piece of paper, but sort of the 2 halves fit one on top of the other. So the thickness then would be 1 millimeter. Then if you folded it again, it would look like 4 sheets were stacked one on top of the other. So the thickness is doubling. Every time you fold the paper in half, you are doubling its thickness. So this is what the sequence would look like: 0.5, 1, 2, 4, 8, etc. So this is a geometric sequence. If you wanted to know the thickness after 4 folds, just be very careful, because you'd be tempted to look for the 4th number in the sequence. But remember that the first number in this sequence, 0.5, that's when there are no folds. So if you want the thickness of the paper after 4 folds, you're actually looking for the 5th term. The 5th term in the sequence is 8. You could work it out using the AR to the 4, because that is the 5th term of a geometric sequence. And AR to the 4 is 0.5 times 2 to the 4, which is 8. So after 20 folds, that would be the 21st term in the sequence, and the 21st term is AR to the 20. So you could put in your A and your R power of 20. Question C, state one reason why this might be an unrealistic model. They're suggesting here it's impossible to fold a piece of paper that many times, so the model is unrealistic. And what you'll find with a lot of models is that models usually only work well for a certain amount of time. So this model might work really well for the first 5 folds, but after that it might not be very useful, because you might not be able to fold the paper over and over again. And that happens a lot with models. Usually they work really well for a period of time, and then they stop becoming useful or effective. Here's another example. Bruce starts a new company. In year 1, his profit will be £20,000. He predicts his profits to increase by £5,000 each year, so that his profits in year 2 are modelled to be £25,000, and in year 3, £30,000, and so on. He predicts that this will continue until he reaches annual profits of £100,000. He then models his annual profits to remain at £100,000. Calculate the profits for Bruce's business in the first 20 years. So if we were going to start writing out a sequence to show the profits, it would start off with 20,000. That's year 1, then 25,000, then 30, etc. So this is obviously an arithmetic sequence. The first term is 20,000, and the common difference is 5,000. That's how much you expect it to go up by each year. So if you wanted to work out his profits for the first 20 years, your first thought might be, well, let's use the SN formula for arithmetic sequences, and let's find S20. And that's going to find the sum, or how much profit is made in total over 20 years. The only problem with that is that this arithmetic sequence isn't going to continue in the same way forever. He thinks that once he gets up to 100,000, it won't carry on increasing by £5,000 each year. He thinks it's going to stay at 100,000. So what we really need to work out is, when will he hit this profit of 100,000? Will it be within this first 20 years or not? So it's really important that the first thing we work out is, when will he hit a yearly profit of 100,000? So what term number will he be on in the sequence when he hits that number, 100,000? Remember that the nth term, let's call it the nth term of an arithmetic sequence is a plus n minus 1d. What we're trying to work out is, what will the term number be when his profits are 100,000? So if I put 100,000 and then the nth term formula, substitute in the bits that you know, we know A, we know D, we can then solve that equation and work out what n has to be. And it turns out to be 17. So we figured out there that he will hit this £100,000 profit after 17 years. After that then, his profit's going to be £100,000 every year. So going back to what I was saying earlier about finding S20, that's not going to work for this question. What we need to do is, we need to work out the sum of the first 17 years using the S17 formula, because for 17 years the sequence will be arithmetic, and then for the years after that we'll just add on £100,000. So using the SN formula for arithmetic sequences, we can find the sum of the first 17 terms. So just using the formula for the sum of the first n terms for an arithmetic sequence. The sum of the first 17 numbers comes to 1,020,000. And then after that then, we just need to add on £100,000 for years 18, 19 and 20. So that's why they're adding on 3 lots of 100,000. That's for year 18, year 19 and year 20. And then we end up with Bruce's final total. This is how much profit he's made in total in 20 years. Part B of this example says, state one reason why this may not be a suitable model, but it's very unlikely in any business that the amount of profit that you make will be exactly the same each year. There are lots of different reasons for that, things like inflation, depends on how well the business is doing, whether they're making a lot of sales or not. There's lots of different reasons. It's very unlikely that the profit will remain exactly the same for so many years. Now in question C, Bruce's financial advisor says that the yearly profits are likely to increase by 5% per annum. So rather than by a constant number, the financial advisor thinks it'll increase by a percentage, 5%. So using this model, calculate the profits for Bruce's business in the first 20 years. So if it's going to increase by 5%, if you think about compound interest examples, if you want to increase something by 5%, you would multiply it by 1.05. And we can use that idea here. So the sequence will start with 20,000. The next term will be 20,000 times 1.05. And then the next term will be 20,000 times 1.05 squared. We're going to multiply by 1.05 every time as we move along the sequence. So this now becomes a geometric sequence or series. The first term is 20,000 and the common ratio is 1.05. So if you wanted to find the sum of the first 20 terms, because that's the total amount of profits over the 20 years, that you can use the SN formula for geometric sequences, put in all the things that you know, n as 20, we know A, we know R, and we can work out the sum of the first 20 terms. So in total over 20 years, the financial advisor thinks that Bruce will make this much profit.